a variation in the UI. Okay, so now you will use the principle of least action, and it says that the variation is stationary, so you set this to 0. And now you use the arbitrariness of the variation in y just a moment, and you conclude that this term must be 0. So the equation of motion governing the string is equal to rho y double dot. And you recognize that as the wave equation, which of course would govern the string.
Can you write in conventional notation that you might be familiar with 350 and they can identify that as a wave equation?
Now in 350, we always had this term called the frequency, right? So, and we can define something like that here. Okay, so maybe we can combine these terms, and this is rho over t. And think about what is the dimension of rho over t. Okay, this is linear mass density. So this is, the rho has unit of kilograms per meter, right? And the tension has unit of Newton. So this thing is kilogram per Newton meter, which is what? Kilogram per joule. I think this turns out to be 1 over velocity squared, right?
It has to be.
Yeah. So
otherwise it wouldn't work.
Otherwise,
can you explain why the atoms disappear again? The two atoms, you drop them, you cross the two atoms out. Can you explain why
okay,
they
so
disappear?
actually they disappear because of quite different reasons. Okay. Now this one, the n terms in the integrated outputs in time disappear because we require the motion of the string. So say consider this. We have a string that's fixed at endpoints 0 and L. Okay. Let's say that at some time t1, I take a snapshot of the string, okay, and it looks like this. So I require that the string looks like this at t1. Okay, so the variation in the string will be 0 at t1. This is one requirement. And then at a later time, I take another snapshot, and I say maybe the string now looks like, maybe it looks like this. And I require that the variation to vanish because the string is required to look like that at t2. Okay, so this is why the integrated out pieces in time vanishes, but it vanishes in x because we are requiring that both ends of the string are fixed. In your homework this week, you will investigate what happens if we allow one end to be loose and then we attach a ball to it, a ball with mass m. Okay, so the whole system, we're going to analyze a ball with mass m attached to a string with one end loose. Okay. So in that case, you just keep on these terms. Okay.
And before you move on, why don't you write down the velocity for the wave in terms of rho and t,
Okay.
and draw some physical interpretation.
So look over here. We have a we have derivative with respect to the spatial coordinate twice over here. So there's something over here that has the 1 over meter squared unit here. But over here, we're taking the derivative with respect to time twice. So there is something over here that's 1 over t squared. Right? So the convergent factor between them must be 1 over e squared. Right? So we conclude that this rho over t thing is some kind of inverse velocity. Inverse velocity. Okay, so we can define the v velocity, some kind of a velocity to be square root of t over rho. Okay.
So you can say something about this from your daily experience. Say if you have a guitar, and if the mass density of the guitar string is very high, it means that the velocity of the sound wave from the guitar string will be very slow, and that will make the tone of the guitar string very low. And T is some kind of representation of how taut, like the Hooke's law. how stiff the string is. If the string is made of very stiff material, K will be big, and then T will also be big. And then the velocity of sound on the guitar string will be very high. So you can actually achieve that by increasing the tension of the guitar string. And you get a higher pitch or higher note on the guitar string by increasing T. So you can actually see this kind of physics in your daily experience when you play the guitar.
Okay, and in connection with what we talked about earlier in the linear atomic chain, if we think about sound wave propagate, this tells you that sound wave can propagate in a linear atomic chain, and that's how it does in a solid. Okay. So for if the atoms are more massive, then from this equation you see that the sound velocity in there will be slower. If the bonding mechanism, which determines T, is the same between two solids. Your question?
Can we model if the string is held at an arbitrary initial condition, like say a triangle condition? How would that evolve?
The initial condition, the specific shape of the initial condition does not enter this.
Okay, this is a steady
But the derivation of the, no, not the derivation, not the steady state. The derivation of the equation of motion just assumes that the string assumes some initial shape, but it doesn't have anything to do with the functional form of that shape. Okay. What that would, so now you derive the equation of motion, we know how to solve this, and to solve this we would impose the initial condition of this. Right? So say for a triangle, you would Fourier transform that and solve this equation. Frequency domain. But the derivation of the equation of motion doesn't need to assume any shape. It just says that at a T1, it's fixed at one shape. Okay? But the D1 is not that. Okay? So are there any questions regarding this this derivation? No? Okay. If not, let me make some comments. Okay. So now typically, notice that what is the there are two coordinates here. One of them is y, one of them is x. Okay? So we know that y is a dynamical variable because it's one of the coordinates. But what is x? What is the role of x in this case? It is actually just an index. If you go through the transition to a continuum, you find that x is just an index. So x has really no physical meaning, has no dynamical significance on the string. It just indexes where we are on this string. Okay. And so what is this y? The y has a special meaning now. This is a more special coordinate than its x. Okay. And for the string, this is the simplest example of what we would call a field. Okay. And it's always the case that if you have some kind of a field, so what is a field? A field is a general function of space and time. Okay, so it depends on the spatial coordinate x, and then it depends on time. Okay, so now it's always true, almost always true that if you construct the time derivative of a field, that's going to correspond to some form of a kinetic energy. Okay? And how the field is distorted corresponds to some form of potential energy. Now in your homework, I ask you to take this analogy to the case of a field that you should all be familiar with, the vector potential. Okay. So we know that the vector potential, the time derivative of the vector potential gives you the electric field. Right. And the spatial derivative, well, it is the curl of the vector potential gives you the magnetic field. Okay, this you should know from your E&M knowledge. So now I'm going to say that the vector potential is some kind of a field, and its time derivative gives you E. So the energy associated with the E field can be likened to a kinetic energy. And the energy, and this shows how the field associated with the vector potential is distorted in space. Okay, and that gives you the magnetic field, and the energy associated in the magnetic field is some kind of a potential energy. So you're going to use this analogy to derive Maxwell's equations in your homework. Okay? And I think that's all we wanted to say.
Yeah, you might want to mention that those equations you write down from 350 only valid when you assume that phi is equal to 0.
Okay, yeah. This is what we call in the axial gauge. Phi anyways, so the vector potential is defined so that its curl is equal to B. B is the physical field, right? But then if we have a magnetic field, and we only know the vector potential to an arbitrary gradient of some scalar function. Okay? So I can add to the vector potential the gradient of some scalar function phi, and that wouldn't influence my magnetic field. That would come up in the electric field, but that would be part of the charge. But anyways, so we're choosing the gauge here to be that phi is equal to 0. And this is only valid in that gauge. All right, so I guess next we're going to talk a little bit about linear algebra. And the only, really, we assume that you guys have all learned linear algebra before. So the only little piece of linear algebra I want to review with you guys is what is the meaning of the function of a matrix. Okay.
So you might want to ask, how many of them have not had linear algebra before?
Yeah, is there anyone here? Is there anyone here who has never had a course in linear algebra before? You have not had one? Anyone else? Okay, so if you need specific help with linear algebra, you can talk to me after class, and then I'll go through some of the basics with you. But okay, so say we have a matrix, okay, and to distinguish a matrix as a vector, I use two bars. And we have a matrix, and we want to ask what is the meaning of a function of the matrix. Okay. So just remember now, this expression only has meaning when it operates on some vector. Okay. Now, say if this was an eigenvector of the matrix, and let's call that what's a good let's call that E. Okay. The ith eigenvector of the matrix associated with the eigenvalue lambda I for that matrix. Okay. Then if V was an eigenvector of the matrix, we can Taylor expand this matrix into a polynomial form. And that would be, you would have the identity in the middle, and then the linear term, okay, and then the quadratic term. I don't want to write out the dependence there, because I forgot. Okay, and then the cubic term, etc. And then all of these are going to operate on your eigenvector. Okay.
The arrow is usually reserved for 3 vectors, since you are describing a vector of general.
By general, okay. So
maybe
let me just use a bar. Okay. So what Professor Chu just stressed is that the arrow, say if I have a vector like this, this is usually reserved for to refer to a vector in 3 dimensions. Okay, but this can be since we didn't specify what is the dimension of A and B. This can, in general, we're going to use a bar to denote a vector. Okay, so now each of these matrices is going to see the vector and it's going to produce its eigenvalue and lower one of its powers, right? So this matrix vector product turns into a eigenvalue product. Okay. So now, if we again sum this back, and this is just.
No, I think you should also define for the sake of some people what an eigenvalue, eigenvector is before you proceed.
All right. So the eigenvalue and eigenvector are defined as I have some matrix A, and the action of its of a matrix on its eigenvector is such that say it operates on its eigenvector, then it only scales this eigenvector. Okay. It scales it by a number. And it can be, and in most cases, we only consider a real number. Okay. Is that clear? So So let me, what happens if this is not an eigenvector? Okay. You can think about, say, an arbitrary vector. Okay. And let's say that the A has some property. It has a complete set of eigenvectors, meaning that for the dimension we're talking about, any vector, any arbitrary vector, can be expanded onto the eigenvectors of A. So we can then write this as an expansion summation over I. Okay, and the AI will be given by the inner product between the vector and so this is the projection of the vector onto the I.
And some students might not know this knowledge. Can you elaborate on this, because it needs like orthogonality of the eigenvectors in order to do that projection? Maybe you just talk a little bit about eigenvectors before you write down the solution there.
Okay.
They have to be orthogonal before you can do the projection. Like
So-
Fourier series expansion.
Okay. So a special type of matrix is called a Hermitian matrix. And the Hermitian matrix have a very nice property is that they have a complete and orthogonal set of eigenvectors. Okay. And how should I say that? And the condition for the matrix to be a Hermitian is just that you have some set of eigenvectors, and this vector is such that for an arbitrary vector in the space, V can be expanded in this fashion. Of course, you know that the Hermitian matrix has this property too. In terms of the matrix itself, we say that its adjoint is equal to itself. Okay. And you can find a book and look for the proof. If this condition is satisfied, then you are guaranteed this. You're guaranteed that you have a set of complete and orthonormal eigenvectors, each with a real and distinct. Okay. So now, say we have a Hermitian matrix, and say it operates on any arbitrary vector. We can compute this by expanding the arbitrary vector onto the basis formed by its eigenvectors. So what is then? Then what is the action of the matrix on this arbitrary vector? If it's not an eigenvector, then you see that we first project the eigenvector, decompose it onto the we first decompose this arbitrary vector onto the space of the eigenvectors. And then the matrix is going to scale each direction differently. So the result would be, it's going to rotate the eigenvector and scale it. Okay. But for the arbitrary vector, it's going to be rotated by the matrix, and it's going to be scaled differently in different directions. Okay. But that's not the case for an eigenvector. For an eigenvector, the action of a matrix is purely scaling. Okay. So that is the essence of, I think, linear algebra understanding for its use in quantum mechanics. So now, getting back to this point, we can now combine these back into the function, but now the argument is going to be the eigenvalue.
So you might want to, for the benefit of some students, explain what a squared and a cubed mean. What is the a to the power of 3 means when a is a matrix, right? It may not be clear to some students.
All right.
Even though.
So this is a matrix, okay? And then the matrix is defined only through its action on a vector B. Okay. Now, what is the square of that matrix? That is twice this action. Okay. So this would be defined as the square of the matrix. Why do I write this down? Because, well, in normal representation, the matrix is a row and column of numbers. Right? Okay. And say we want to define matrix multiplication, but there are many ways to multiply together, two things. Well, let me just remind you that matrix multiplication has this meaning. So the rule, the algebraic rule for its for how it should be carried out should be determined by this meaning. Okay? And that rule turns out to be you take the first column over here, multiply it by the first row, produce a number. That gives this first entry, say this is the 1 entry, etc. Okay. But keep in mind that why do we do this matrix multiplication? It's because we want the matrix multiplication to have this meaning. Okay. And we can have other operations, and then the operations will have other meaning, and then you could define matrix multiplication in other ways. But this is what is meant by a squared, a cubed, etc. Is that good?
Yeah, maybe it's within a 5 minutes break.
Okay, that's good.
We can continue. Are there any questions on so far what Ian has said? Yeah, you wait.
It's an expression for the function of A.